Hello all, welcome back to Electronic Devices and Circuits video lecture series. I am BV Sachinarayana, Associate Professor in Department of ECE, Eastern Institute of Technology, Bhimavaram. In unit number 3, Rectifiers and Filters, we already discussed about introduction, basic rectifier setup, half-wave rectifier operation and waveforms, center-tapped full-wave rectifier operation and waveforms, bridge rectifier operation and waveforms, half-wave rectifier characteristics, and some of the center-tapped full-wave rectifier characteristics such as IDC, VDC, and IRMS. Now, in this video, we will discuss about the center-tapped full-wave rectifier characteristics such as DC power output PDC, AC power input PAC, rectifier efficiency eta, and ripple factor gamma. The objectives of this lecture are derivation for DC output power PDC, derivation for AC input power PAC, derivation for rectifier efficiency gamma, and derivation for ripple factor gamma. DC output power. The amount of DC output power can be delivered to the load by using the center tapped full wave rectifier. Now I am trying to calculate. DC power output PDC can be calculated by using the general expression P equal to VI. Now I am trying to calculate the DC values. That's why DC power output equal to EDC into IDC, or we can call it as a VDC into IDC. Since VDC equal to IDC into RL, if you substitute IDC into RL in place of VDC, then we are getting IDC square into RL. So the DC output power can also be calculated by using this IDC square into RL. And we already calculated IDC of center tapped full wave rectifier, which is given as IDC equal to 2Im by pi. Substitute this IDC value in this expression, then we are getting 2Im by pi whole square into RL, that equal to 4 by pi square into Im square into RL. And we already calculated the peak value or maximum value of the load current, which is equal to Im equal to Vm by Rs plus Rf plus RL, where Rs is the secondary winding resistance, Rf is the diode forward resistance, and RL is the load resistance. Then substitute this Im value in this expression, then we are getting PDC in terms of Vm. So PDC equal to 4 by pi square into Vsm square or Vm square by Rs plus Rf plus RL whole square into RL. So that is the DC output power delivered to the load in terms of voltage. So if you compare this PDC with the half-wave rectifier, then PDC of half-wave rectifier is equal to Im square by pi square into RL. So we can say by using this center tapped full wave rectifier, the DC output power delivered to the load is increased by 4 times. So we can write PDC of full wave rectifier is equal to 4 into VDC of wave rectifier. Because of center transformer action, and two diodes, there is a load current for both positive and negative off cycle. So the output power delivered to the load is increased by 4 times compared to the off wave rectifier. AC input power. Now I am trying to calculate what is the input power supplied to the center tapped full wave rectifier. So AC input power PAC equal to, again by using general equation V into I we can calculate. So very clear, V equal to IR. So you can substitute IR in place of V, then we are getting I square into RL. Since I am trying to calculate AC power, the current it is expressed in RMS value, and the resistance are, there are three resistances we need to consider in center tapped full wave rectifier: RS, RF and RL. And hence the AC input power supplied is equal to IRMS square into RF plus RS plus RL. And we already calculated IRMS value, that IRMS value equal to Im by root 2 for center tapped full wave rectifier. So substitute Im by root 2 in place of IRMS, then Im by root 2 whole square into RF plus RS plus RL. Then our PAC equal to Im square into RF plus RS plus RL by 2. Then substitute Im value. Im we already calculated, that Im equal to Vm or Vsm by RS plus RF plus RL. So substitute Im, then PAC equal to Vsm square or Vm square by RF plus RS plus RL whole square into 1 by 2 into RF plus RS plus RL. Then the final expression for PAC equal to Vm square by 2 into RF plus RS plus RL. Then rectifier efficiency. Rectifier efficiency is defined as the ratio of DC output power delivered to the load to the AC input power supplied. So this rectifier efficiency represents how much AC input power is converted into the DC output power. So rectifier efficiency is equal to DC output power by AC input power. We already calculated DC output power and AC input power. Substitute DC output power and AC input power in terms of Im. Then our efficiency eta equal to 4 by pi square into Im square RL by Im square into RF plus RS plus RL by 2. And if you manipulate this equation, then this Im square and Im square, it is cancelled out. So eta equal to 8 RL by pi square into RS plus RF plus RL. So here RS and RF are the internal resistances of secondary winding and diode forward resistance. Both are very small compared to RL. So RF plus RS is far less than RL. So we can neglect RS plus RF. Then our eta, it becomes 8 by pi square. So if you calculate 8 by pi square value, then we are getting 0.812. So in general, efficiency is expressed in percentile, so it must be multiplied with 100. So the center tapped full wave rectifier efficiency is 81.2%. Whereas for off wave rectifier, the efficiency is equal to 40.6. Means here the efficiency of center tapped full wave rectifier is doubles that of the off wave rectifier. In off wave rectifier, there is no load current during negative off cycle, whereas in center tapped full wave rectifier, there is a load current in negative off cycle also. That's why the efficiency is doubled. Means here in this center tapped full wave rectifier, more AC is converted into DC. So we can say 81.2 percentile of AC input power is converted into DC. Then the next parameter is a ripple factor. So ripple factor is defined as the ratio of AC component to the DC component of the rectifier output. So this ripple factor is equal to AC component by DC component present in the output. And we already derived the general expression for ripple factor in off wave rectifier, which is given as square root of IRMS by IDC whole square minus 1. So we already calculated IRMS and IDC for center tapped full wave rectifier. IRMS equal to IM by root 2 and IDC equal to 2 IM by pi. If you substitute these two values in the general expression, then ripple factor gamma is equal to Im by root 2 by 2 Im by pi whole square. And this Im and cancelled out. Then ripple factor gamma equal to square root of pi square by 8 minus 1. If you calculate this value, then we are getting ripple factor gamma equal to 0.81. Whereas the ripple factor of off wave rectifier is equal to 1.211. So for off wave rectifier, gamma value is greater than 1, whereas for center tapped full wave rectifier, the gamma value is less than 1. If gamma value is less than 1 means there is very less AC component present in the output of center tapped full wave rectifier. So as the efficiency of center tapped full wave rectifier is more DC is present in the output, and hence the AC component is less. That's why the gamma value is less than 1. So we can say AC component present in the output is equal to 0.48 into DC component in the output. Means there is very less AC component present in the center tapped full wave rectifier. Then coming to the summary, in this lecture, we derived the expression for DC power output PDC, AC power input PAC, rectifier efficiency eta, and ripple factor gamma. In the next lecture, I am trying to derive the expressions for peak inverse voltage PIV, transformer utilization factor TUF, load regulation, peak factor, form factor, and at the end I'm trying to explain advantages and disadvantages of center tapped full wave rectifier. Thank you all.